Hello, welcome to week 3 of our subject climatology. In this week, we are looking at boundary layer climates. So we will start with defining boundary layer. Then we will look at surface energy budget and how these various surfaces they interact with the energy. So we will be looking at rocks and sand, water, snow and ice, short green crops, forests, and urban areas. So firstly, let's define what is the boundary layer. Boundary layer is the lowest part of the atmosphere. It is also known as planetary boundary layer or atmospheric boundary layer. So you can see it is the region of lower troposphere where Earth's surface is basically uh, influencing temperature, moisture, and wind through turbulent transfer of air mass. Uh, you might have seen top of the boundary layer indicated by a very thin layer of haze when you are on board an aeroplane during takeoff time. And air within this boundary layer during the day is thoroughly mixed because of convection, which is induced by heating of Earth's surface. And we know that convection is transfer of heat due to bulk movement of molecules within gases and liquids. If we look at the top of the boundary layer, it is characterized by sporadic and weakening turbulences. The thickness of boundary layer it depends upon various factors. Typically, the boundary layer is about 1 kilometer thick, but it can vary from 10 meter to 5 meter. Because thickness of boundary layer, it depends upon intensity of surface heating and amount of water evaporated into air from the Earth's surface or specifically the biosphere. In general, the greater the heating of surface, the deeper the boundary layer. Over deserts, the boundary layer may extend up to 4 to 5 kilometers in altitude, whereas boundary layer is less than 1 kilometer thick over oceans because of little surface heating. This little surface heating is because of the vertical mixing of water. Generally, you can see that for every 1 degree centigrade increase in daily maximum surface temperature, the top of boundary layer is elevated to 100 meters. Seasons also impact boundary layer height. For instance, during spring over forest areas, it will come down about 200 meter to 300 meter. But when the season of warm season will be beginning, it will again rise. The boundary layer is very important for us, the climatologists, because it has an important influence on the behavior of atmosphere as a whole. So we need to represent the boundary layer properly while performing climate modeling or numerical weather prediction, particularly for the variables such as near surface wind and turbulences, daily maximum and minimum temperature, visibility and fog, pollutants, and other materials. So if we look at the atmosphere of the Earth, you can see that boundary layer is about this length, right? And a lot of atmospheric activities are happening in this boundary layer. I hope this is clear. So now let's look at the surface energy budget. We know that net radiation is equal to sensible heat flux plus latent heat flux plus ground heat flux, or you can write it as Q star. The same equation, this we have seen already. So now see, let's revise how the heat is transferred. there are basic three categories of transfer of heat. Firstly, let's look at this example and explain all these three. In case of radiation, we know that radiation doesn't require any medium because we have seen the solar radiation, which is electromagnetic radiation, and it can pass through space. So if we are even keeping this pan at a distance from the top of the stove, still the heat is being transferred and we have this water being boiled after some time. So this is radiation. And if the handle is this handle is metallic, you can see that we can feel the heat which is coming from a distance, and it is traveling, the heat is traveling through this pan, and our hand will be warm after, will be feeling this heat very soon. So that is the conduction. That is, energy is moving without material being moved. The third is convection. So energy moves with material. So you can see these bubbles will start to rise and the heat is being transferred. And after some time, the water will start evaporating. So that air is basically moving upward. So heat is also traveling. So you can see here the example of heat transfer through convection. Warm air rises, and so heat is basically transferring through the warm air. This is known as convection. And if the warm air molecules, they move horizontally, that is known as advection. Okay, so now let's look at the sensible heat and latent heat flux. Sensible heat is basically the heat is transferring and the temperature is also being changed. The example is when we sit in the sun. So how much our temperature is increased, it will depend upon the amount of energy and the specific heat. For example, if you are sitting in the sun when the sun is right on top of us at noon time, so we will be having more, we will be feeling more heat. And the other thing is the specific heat. Specific heat is the energy needed to raise the 1 kilogram, raise temperature of 1 kilogram of a substance by 1 degree centigrade. Water has a high amount of specific heat, which is about 4,200 kilogram for a degree centigrade or for a unit of temperature. That is why you see we feel when we are swimming on a hot day in the sea, sand is very hot as compared to water because sand has very low specific heat as compared to water. So if you look into the day and night time change of temperature, it's because water has high specific heat, so it is not emitting too much as compared to the land masses, which have very low specific heat because of the various land uses. We have urban areas, we have agriculture, we have deserts, so a lot of diversity is there, right? But in the ocean dominating areas, there is very less amount of change, less degree of change between day and nighttime temperatures because of this specific heat of water. So now let's look at latent heat flux. Latent heat flux is transfer of energy which causes change in phase. So there will be one point when we are changing the phase of a substance when the temperature will not change, but energy is stored. That is known as latent heat. And if we are changing from water to water vapor, that will be known as latent heat of vaporization of water. So that heat is about 22,500 kilojoules per kg. So let's look at a graph to explain it more. For example, you have an ice and you are heating it, you are supplying energy and you are heating, so you are increasing the temperature. So when the ice will be at 0 degrees centigrade and we keep increasing the temperature, we keep increasing, supplying it energy, we keep supplying heat, the temperature will not rise. So that amount of energy is being absorbed and that will be utilized to change solid to a liquid. So solid water to a liquid water. So you can see then its temperature will rise quite quickly till we will reach 100 degrees centigrade, but still it will remain there. We will not be increasing further the temperature while the supplied heat will be absorbed, and this heat is known as latent heat of vaporization. And when this heat is absorbed, this amount of heat is absorbed in the water, that will convert it into the water vapors. And same process is the reverse. The only thing is when we have condensation, the energy is released instead of being absorbed. So we will have a cooling effect, right? So example is when you run on a hot day, you are sweating, and when your sweat evaporates, you feel a cooling effect because your heat energy is being absorbed. The body's heat is being absorbed to release the water vapor into the gaseous stage, right? So your heat, that heat is being absorbed to make your sweat evaporate. So you will have a feeling of evaporative cooling, right? So what is happening on our land masses? So if we see that maximum radiation is on the equator, and the regions around the equator, they are hotter. So there the heat is being absorbed and a lot of water evaporates in those areas. And these areas are mostly drier areas. You can see that we are also in this region, right? So more evaporation is happening. So these are also known as evaporation latitudes because heat is being absorbed here. And as we go towards north and south, we have heat energy being released because we have precipitations here, a lot of precipitation here. Right, so the next is now let's look at surface energy budget, and let's quantify sensible heat and latent heat flux. You can quantify these using these formulas. In case of sensible heat, we know that change of temperature is important. And in case of latent heat, we know that pressure is important. So change of pressure is there. Rest are the constants. Rho, for example, rho is the density of air, which is fixed, 1.2 kg per meter cube. Cp is the heat capacity of air. This is also constant of 1010 joules per kg per centigrade. Delta T is change of temperature. Delta T is change of vapor pressure. Gamma is psychometric constant, K, which we are also using in our Bowen ratio. So Kh and K nu are turbulent transfer coefficients. Kh is for the heat and K nu is for the water vapor. So now we can compute Bowen ratio by we know that Bowen ratio is basically ratio of sensible heat and latent heat. So beta is the Bowen ratio, H divided by LE. So we can divide these two equations. So here we can reverse the denominator here for ease of calculation. And now you can see that we can divide. The only thing important to know is KH and K nu, both are identical. So we can cancel these as well to get delta T over delta E times gamma, which is the psychometric constant, is our Bowen ratio. So if we have Bowen ratio, then we can compute latent heat in our energy budget. So we can substitute H from this equation. So that will be net radiation is equal to latent heat times beta plus latent heat plus ground heat flux. And we can come to this equation, which is the latent heat. So if we have latent heat, we can convert it in watts per meter square or joules per second per meter square. We can convert into millimeter. And if we divide this with the latent heat of vaporization of water, we will get our evaporation. So latent heat of vaporization, we know that it's a constant, which is 2,500 kilojoules per kg. Right? And then in energy balance, we can extend when we have different surfaces. So the energy will be stored in those surfaces, such as delta S is the heat storage and delta A is the advection of heat, which is horizontal movement of heat with the air. There can be other storages as well. For example, if we are looking into the plants, we know that plants, they perform photosynthesis to produce their food. So they are storing chemical energy in their leaves and stems, depending upon, even roots, depending upon the nature of the plant. So that is the chemical change of chemical energy using this surface energy. Because remember, photosynthesis happens in the presence of radiation, the sunlight, in natural environments, right? So now what we can do is we can look into a strategy, how to read surface energy balance vis-a-vis change of the surfaces. For example, to simplify, we have put here three conditions. So in first case, we have a very mild water stress. Then in this middle, we don't have any stress, rather the water is being supplied through artificial irrigation. Artificially, so that is the irrigation. So, and then we have very dry conditions. So in this case, latent heat is equal. First of all, you can see the intensity of net radiation. That is same, almost the same magnitude for all these conditions. And ground heat flux is also same, though when we have very dry conditions, the ground heat flux will be a bit more, right? What is being changed? The two things, latent heat and sensible heat. And that makes sense because there will be evaporation and different amounts of evaporation in different conditions. So we will have different amounts of latent heats and contribution or sensible heats. So we will have different contributions of these two latent heats and the sensible heat in our net radiation. So if we have very mild water stress, canopy of temperature will be greater than air temperature, but still we will have evaporation and we will have sensible heat, and these two are equal. And since these two are equal, it means that we will have a Bowen ratio of 1, right? So if we go into the no water stress state, so latent heat will be more than sensible heat. Canopy temperature will be less than air temperature. So when we see this type of condition, that we have a lot of evapotranspiration, or in other words, we have a good amount of latent heat, whereas we have negative sensible heat, it means that there is more evaporation, and hence we will have Bowen ratio less than 1, and in some instances it will be negative, in negative, in case of this kind of situation, which is well-watered system. And the Bowen ratio is increasing when we are going to dry conditions. And if we go to the very dry conditions, we will see that there will be less evapotranspiration and lot of sensible heat. So the surface temperature is much greater than the air temperature in this case. And in the dry conditions, then if you look into the natural habitats, you will find in these type of conditions, if we have vegetation, it has evolved in a way that it needs very less water because there is low evapotranspiration. So they will not be able to utilize sun energy to produce their food. So they have changed their phenologies in a case. So this is how you will be looking into interaction of various surfaces with the surface energy balance in the boundary